Okay, so today I hope is going to be our last day of doing these parametrized surfaces because we have a lot more things to do this semester, a lot of really fun things. I've asked the president of the university to actually come to one of our classes. He emailed all the instructors this semester and said, would you like me to come and sit in on a class and just, be part of the experience? And I said, yeah, come to our class. That would be awesome. So we'll see. But if that's the case, I want to do some cool stuff when the president's here. So we got to get through this stuff, which is also very cool stuff. So without further ado, let's talk about finding the area of a parametrized surface. So that's what we'll do today. I'm going to draw a little picture about really what a parametrization is. You've seen me do this picture a couple times, and I hope you're comfortable with it now. Remember, you've got a little square or a little rectangle in the UV plane. I mean, typically your U is weighing 0 to 2 pi. So your A is 0, your B is 2 pi. And you've got these horizontal lines and these vertical lines. And I also was going to tell you that after this next written homework is coming up, which is going to be a homework about parametrizing, coming up with parametrizations, computing the vector fields, yada, yada. I'm going to upload a notebook I made, and it contains basically every parameterization you'll ever need to know. So it's something for you to look back and reference if you need, but that'll come later. That's something I've been working on, and I've been spending time doing nice pretty drawings. Okay, so here's your parameterization. This is X, your Y, your Z, and you get some neat little surface, some squiggly surface in 3D space. And this is what your parametrization does. And so we're doing areas. So, area, you can tell we're inching towards integrals. And integrals always kind of revolve around cutting this domain up into smaller and smaller bits. So let's say I cut this into n little segments. And I have delta u is b minus a over n. And up here, I'm going to zoom in. I'll have m segments. Okay. And this gives me delta v is d minus c over m. All right. Okay. So these are some of the pieces that we'll be using. If you note on the left, we have, this grid of little rectangles, and how those little rectangles look on the right side of the picture are a whole bunch of these little parallelograms. So I'll zoom back out in a second, but here you've got a whole bunch of little parallelograms-ish. They're kind of like parallelograms. As you take your n and m to be small, to be bigger and bigger and bigger, these shapes get smaller and smaller and smaller, and they really start approaching, honest to God, parallelograms. So it's kind of, no. Okay, I gotta be really careful with this. Okay, so what I'm gonna say is that the area of the full surface, I'm gonna call this surface S over here. So the idea to say is that the area of the surface S, that squiggly surface, is going to be a sum of all of the little parallelograms. So I'm going to call this parallelogram Pij. So think of it as you're going out I in the IU steps and JV steps. So this might specifically be P3, 2. But we're going to add up all those. So your I starts off at 1, goes to n. Your j starts off at 1, ends up at m. And I'm just going to add up the area of the little parallelogram. The area of the full thing is about the area of these small parallelograms. Area of Pij. So our next step is what we want to do is I really want to get a good expression for this quantity using my R. So that's their next goal. So goal, write formula for area of Pij. So I'm going to zoom in on what this picture looks like. At this picture, I've got this going on here. Okay, I'm going to label these vertices because really what we'll do is, I know y'all know how to do area of a parallelogram. It's the magnitude of the cross product of this displacement vector and that displacement vector. So that's what we're working towards. So I'm going to use some color coding. Let's start this base. That's going to be I'll just call that R of UI VJ. Okay, then if I want to get to this green point over here, what I'll do is I'm gonna amp up my U parameter by a little change in U. So that green is R of UI plus delta U, but we're on that same line piece, so we're gonna keep the VJ constant. So VJ, okay. And then the same thing is going to happen up on this blue piece. So if I want to start at that red, end up at the blue, well, I'll keep the U constant, but I'm going to amp up my V coordinate by a little change in V. So I'll have R of UI VJ plus delta V. Okay. And I'll even furthermore, all right, this is going to give me an orange vector, and this an orange displacement vector, and this will give me, I like purple, this will give me a purple displacement vector. So now I'm going to write the area of Pi comma j is the magnitude of a cross product of orange vector cross purple vector. Okay, okay, so we're doing that. I hope I hope nothing's too radical here. I mean, what you probably, we've done enough of these Riemann sums that you kind of see what we're going to do is we're going to see something come out of this sum. We're going to, it's going to have some pieces. Then we're going to take a limit and see how that converts to an integral. So that's where we're headed. And that's how we're going to be doing these scalar surface integrals that can compute a surface area of a full thing. So I want to get a good formula for the orange vector. The orange vector is, okay, it's a displacement vector. So it's going to be the green dot minus the red dot as a displacement vector. And if I just write that out, that's going to be, okay, this. I can zoom back out, that's unnecessary. And because that's kind of a long thing to write, I'm just going to call that delta R. So this is a vector. Don't forget, these are all vectors. Delta, in the past we had something like, delta theta. That was a difference of two numbers. That was a number, but really, the R has an X, a Y, a Z component. And so when I take a difference of them, I'm really looking at a difference of X, Y, Z components. And this is the displacement vector. So I'm going to call that delta R for a second. And well, I'll say it in a second. Then the purple vector, okay, this is just blue minus red. So these are displacement vectors. And that's, okay. I'm literally just copying and pasting. I'm just not keeping the colors consistent. R, U, I, V, J, okay. And I want to call that, again, that's like a delta R. And so now my notation's a little messed up because I'm calling the orange vector delta R and the purple vector delta R. That's kind of wrong. So I want to denote that the first one is a delta R with respect as we're changing the U coordinate. So inside, this is not a standard practice, but I'm going to zoom in up here, and on the inside of the delta R, I'm going to write a U to say, okay, we're moving the U variable, and down here is the V. Okay. All right. So I'm going to go to this next page, and I can copy and paste. I've learned how to do this successfully. Okay. Copy. And we're going to go to this next page so that, all right. On page 2, I'm going to, all right. This is what we're doing. And so now we've got the area of Pij is the magnitude of delta UR cross delta VR. Okay. Okay, it's a magnitude of a cross product of displacement vectors. And if you remember what we did in the scalar line integrals, I did this thing where I did a multiply by delta t and I divided by delta t. So we're going to do something very similar because, well, you'll see. So instead of delta t, I've got 2 parameter values. I don't have 1 parameter value. So I'm going to multiply by delta u and delta v and divide by delta u, delta v. So I just want to remind you that because v and u are numbers, delta u and delta v are numbers. So it makes sense that I'm dividing by them. It would not make sense to be dividing by delta ur. That wouldn't have made sense. So again, these are vectors on the inside of a cross product and a magnitude, and these are lengths. These are numbers. And so numbers, they're positive numbers. They can slide right on into the magnitude function. So here I'm looking at, if I slide those things in, I get this. Okay, so this is the area that we're dealing with. This is the area of that displacement parallelogram. And we see, let's see what happens. So let's ask, what happens to these terms as delta u and delta v go to 0? Because that's what we have. That's what we do in the Riemann sum. Right? We take this limit as these pieces get very small. So this red piece, so that will go to the partial derivative as we take the u derivative of each component. And last time we just called that partial u. Same thing's going to happen over here with this. That will become partial r, partial v. We discussed this on Wednesday, and we call that the partial v vector field. Okay, that was those really pretty vector fields that run along in the crisscross manner along your surface. And okay, and by now these things shouldn't be that bad. These things, that's going to run off to du dv in an integral. So the final product, we have that the area of the surface is the limit of the partial sums. So the limit as delta u goes to 0 and delta v go to 0 of the okay, j equals I equals, they start at 1, this one goes to n, this one to m, and let me think. We had area pij. I'm going to copy and paste. Okay. Okay. Equals, now I'm going to erase that formula because we know what area of that thing is. So I'm going to write down that this is magnitude of partial u, not partial u, delta r delta u cross delta r delta v, delta u delta v, and that limit is the double integral. This one's from a to b because that inner one's the u, then this is c to d because that one's the v, of the magnitude of partial u cross partial v du dv. This is the area of the surface. Okay. So what does this mean? It's like we gotta, if we want to compute the area of something after we have a parametrization, we first have to find those 2 coordinate vector fields by taking partial derivatives. Then we need to cross them. and then we need to take the magnitude. And once we've done all that work, we can actually integrate. And so what we say is that the area element for a parametrized surface is this thing, du dv. That's kind of what's going on here. And really, you should think of this as you're doing the double integral of the constant function 1 over a surface. So this is symbolically describing what we're doing. We're doing a double integral because we have two variables, u and v. We're integrating over a surface, which is different than an R. So this is different than what we did like about a month ago when we had flat 2D regions in the plane. Now we have 2D regions floating in 3D space, so it takes much more work. But this is essentially what we're doing. So I'm going to do an example, our very first example on the next page. If there are any questions. Okay. Ah, no. Man. Nope. What am I doing? Class notes. I'm so sorry. Okay, that's this one. Oh, why does it do this? Okay. Good. Okay, I need to find out how to make that not happen. All right. Okay, so let's do an example. Let's do an example of a cone. So find area, surface area of cone. All right. So we've already done the parametrization, so I'll just remind you real quick. It's R of uv is v cosine u, v sine u, and v. I promise we've done this before, and the reason why, I see that v and that v, so in the RZ plane, it does this thing, because that's v comma v, and then I rotate it around. And my u is ranging between 0 and 2 pi, because it's my angular coordinate, it's the thing in the cosine. And my v is, let's say 0 to 1, meaning I'm truncating my cone up here when my v equals z, which is 1. So v equals z equals 1 is that last bound that I'm dealing with. Okay, so that's the cone. And to find the area, I'll remind you what's on the previous page. The area of cone is the surface area of cone is symbolically an integral of the constant function 1 over the surface with respect to the area element. I'm adding up little pieces of area which are weighted by 1. That's how you should read that. There's really nothing. And then if you want to actually decompose it, it's going to be a double integral 0 to 2 pi, 0 to 1 of a cross product du dv. So this is where all the money lies, and it's actually going to take quite a bit of work because we got to think of all the steps. We've got to take partial derivatives, we have to take cross products, and then we have to take norms, or magnitudes. So let's go ahead and just begin this. So partial u, I think we've done this before, but remember I'm looking at my 3 components up here. I'm hitting with it with a u derivative. So I've got negative v sine u, positive v cosine u, and 0, because that last thing has no u's in it. And then partial v is, all right, I got cosine u, sine of u, 1. All right. I'm going to pull that down here, make it a little bit smaller. All right. So we've done those partial derivative, those partial vector fields, and just for sake of good practice, if I make this one my light blue, how you saw this appear on Wednesday, was this looks like these little vectors that run along the quote unquote theta direction, and in the back they go this way, and then those peach vectors are running vertically up the direction of the parametrized thing. So those are these pieces. Okay, what was that? And now our next step is we've got to cross those two. So I know we've probably only we've only taken the cross product of vectors that look like a constant, maybe 1, 2, 3 crossed with 4, 5, 6. We've done that before. which is the same structure, but now instead of having constants as components of the vectors, they're functions of u and v, but structurally it works the same. So partial u cross partial v is, I'm going to give myself a whole bunch of room. Remember, we do I, j, k, and we start covering stuff up. So, it's like I cover this thing up. So I'm doing v cosine u times 1 minus this times that, which is 0. So here I'm getting just v cosine of u. All right. I'm going to do the same thing for that middle one. And it's that and that. So I'm going to be doing this times this minus this times this. And that is going to give me v sine u. So I got really a minus minus of that. And on the last piece, well, I'll actually write it out because, okay, so it's actually going to be negative v sine squared of u minus v cosine squared of u, and this just becomes negative v. So we're looking at, I'm going to factor v out of the entire thing. I'm looking at v times cosine of u sine of u comma negative 1. This is my partial u partial v vector field. This is my cross product. This is my cross vector field. I know it's kind of weird. It's like, what the heck's going on? And we're going to talk about this more. But in fact, I actually want to show you geometrically what the heck is this thing. Because we're going to be doing this later when we do flux integrals. So I'm zooming in up here. I'm looking at that cone. What I've done is I've taken the cross product of, let's pick a spot. I've picked a point. And what are we looking at? We're looking at partial u cross partial v. That's baby blue cross baby pink. Actually, I don't want to start at that point. Let me draw a point right here. Right here. Okay. So imagine we're taking that blue vector and we're taking the cross product with this pink vector. And if I take a cross product, remember the thing that we get is something that's normal to the two vectors. So if I draw that in red, the cross product is going to be coming directly out of the cone like that. And that's the case everywhere. Everywhere I get something that's coming out orthogonally out of the cone. And in a sense, what we've done is we've computed a normal vector field, but we'll discuss that later. That's geometrically what we've discussed, but we don't really need all that information. We just need to take, as you see here, the length, the magnitude of that, because the magnitude of the cross product is the area of the thing, of the spanned parallelogram. So if I want to take the magnitude of partial u cross partial v, this is the magnitude of, I really am into copying and pasting right now. Copy, paste, and I'm going to shrink it down like that. Okay, just copying and pasting. Constants pulled right on out, so that v comes out as an absolute value of v, but look at my range of v, always positive, so I can kind of skip that. It's just a v pops out, and then magnitude of cosine u sine u negative 1. This is v times the root of cosine squared plus sine squared plus 1, and that gives me v times root 2. So that was seriously the money in all of this, in this whole question. We found this red underline thing, and that's what we got to integrate, and then we'll be done. So final answer, the area is a double integral from 0 to 2 pi, 0 to 1. I'm not going to use the copy and paste function, but I would if it were quick. I'm taking that, I'm putting it right on in here. So v root 2, and then du dv. I'm literally copying and pasting. I'm literally using that formula, that as my recipe book. Okay. So this isn't too bad. I'm going to pull that root 2 out, and then I'm going to do that u integral first. That just gives me a time to 2 pi. And then I'm looking at the integral of 0 to 1 of v dv. If I integrate v, well, a power of 2 comes down, and I get like root 2 times pi times v squared evaluated at 1 and 0, and this just gives me root 2 pi. Okay, that's the answer. That's the area of the cone. Okay. So what we've done is we've integrated the constant function 1 over our surface. So in theory, you can integrate different functions over the surface. For example, imagine this piece of cone is made out of some tinfoil, and the tinfoil at different locations has a different mass density, and that's modeled by some function f. If you integrated that function f over the surface, in theory, what you'd be doing is you'd be racking up, or you'd be accumulating the total grams of the surface. So in this case, we weren't dealing with a function. We scaled each piece of area uniformly with 1, and we got the area back. So let's kind of explain what happens when we integrate a function. So let's explore integrating. So we're adding up pieces of area over a surface, and we're going to weight those pieces by a function f. Now I see something in the comments. Where do we get the du dv from? I get the delta's cross product. Okay, let me ask. So Christopher's asking, I'm going to use my highlighter. Is this what you're asking? That spot? You can talk. Yeah, you can talk if you don't mind being on YouTube.
Yeah, I was just confused about the derivation.
On the previous
I think it's on the previous slide where you kind of derived everything out, but I was just wondering where you got the du delta u times delta v from.
Okay, I highlighted it in yellow. Is that the step that you are?
Yep.
Okay, good. I can explain that. So in the previous step, what did I do? I multiplied by constant function 1. I can multiply by 7 over 7, and I don't change the thing, right? So what I've done is I've think of this as like I'll multiply by 7 over 7, and then I've kept 7 on the outside. That's what this yellow piece is, but that denominator has rushed onto the inside. So I really wanted that delta u and delta v to be present in the denominator so that in a limit they would become the partial derivatives. You really need to divide by you have to have a denominator going to 0 essentially. And that's
gotcha.
Yeah, okay.
Cool, thank you.
Yes. Okay. Lori's at 7, and then we'll come all the way back here. 1, 2, 3. Okay. So now we're going to be integrating. I don't understand why du and dv look like on the cone. Are they tangent or perpendicular to it? Okay. So so Nicola's asking a question. I'll draw a better picture. Let me think. Okay, let me put this on pause for a second, and Nicola wants a better picture, which is totally fair. So let me draw. Here's my cone. Here I'll draw. This is a constant u line. It looks like a theta line. And here's a constant v line. And the partial u vector fields are always pointing along the blue lines. And the partial v vector fields are always pointing along the purple line. So these are both tangent to cone. And so if I took the cross product, I like this grass screen. So partial u cross partial v is now going to be completely orthogonal to the cone. So at this spot, it's going to come outwards like this. And I think you can do your right hand rule. Get the finger part of your hand, the 4 fingers, push it along the blue, curl it along the pink, and then the thumb comes out in the green direction. It comes out orthogonally. So that's kind of the picture. And don't worry, we will definitely be coming to that like in a week. Okay, so there's that. I'm gonna put that on pause. That's from previous page. Okay, so what, all right. Okay, so when we set up an integral, it's going to be it's going to feel just like when we did scalar uh, line integrals, where we had a function. Remember, we had like an f of x, y, z. Maybe that was describing density, and we had some r of t, which was x of t, y of t, z of t, and we set up the integral. We did a to b. We had magnitude of r prime of t dt, and we didn't write f x y z. Remember, the whole integral had to be a function of t. So to fix that, I changed my x's, y's, and z's to my actual parametrization, because I wanted to know the value of the function where the curve was. So the where is described by these three functions. So I did a, b, f of xt, yt, zt. Then I completed the whole thing. This was r prime dt. Okay, and so now this was a total function of t. Same thing is going to go for ours. So for scalar surface integrals. So for a scalar surface integral, so symbolically, we're adding up pieces of area over a surface, and we're weighting each piece by a function. And how does this look? Well, we'll do a to b, c to d. This is dv, du. We need that area piece, and so that is we said that was a magnitude of partial u cross partial v, and you might want to just write f of x, y, z, but you're not quite done at that point, because remember, this integral you better only be seeing u's and v's in it before you can start rolling up your sleeves and going back to math 102 and doing the integral. So to fix it, again, where you'll substitute x for x of uv, y of uv, and z of uv. So this really becomes, so I want to evaluate at location r of uv. And this is going to take me probably 60 seconds. So cd a b f of x of uv, y of uv, z of uv. This looks like a total mess, but in our example, it won't be so bad. My f won't be so crazy. Du dv, and that is like your recipe booklet for how to set up and evaluate a scalar surface integral. So I'm going to copy and paste this, take it to this next page, and give you an example of a surface and a function, and we'll do this. Okay, this is page 5. Okay, so that's the formula we'll be using on this page. So let's do an example. The top of a wine glass is modeled by a parabolic bowl, which is z equals x squared plus y squared, and z is below, let's say, 1. So the picture looks something like this. That's my parabolic bowl. So we're going to need to come up with a parametrization of it. That's okay. It's in your notes somewhere, so we won't spend too much time on it. I promise it's in your notes. And the glass density, the mass density of the glass is f of x, y, z is z squared grams per centimeter squared, where x, y, z are measured in centimeters, I guess. It's a very tiny glass because it's only 1 centimeter tall. That's fine. Maybe it's for a mouse or something. All right, so what this means, what I'm telling you here is that this is my wine glass, and at the bottom, here's z equals 0. It's basically has no density at all, basically, whatever. But as you move up higher, as your z value increases, the glass gets heavier and heavier and heavier. It's kind of really a poor design for a wine glass, but that's okay. So it's heavier here, heavy up top. And so we're going to do a scalar surface integral that computes the total mass. So what is total mass of wine glass? Okay, so step one. So it's like, so really we're going to be setting up an integral that does this. It's going to be a double integral over the surface with f dA. So step one is the S, parametrize S. Step two is going to be, and you know, all of these double, triple integrals, whatever they are, it's always 3 steps. It's like figure out the bounds. So in that case, it's the hard case when you're parametrizing the thing, you know, finding the bounds, then getting the area or volume element. And then the last one is going to be writing the function in your coordinates. So I'm literally gonna write these steps all out. Step 2 is compute, I like colors. So compute dA, which is going to be a magnitude of a cross product. And then finally, step 3 is going to be the F. So write F in terms of u, v coordinates. That's step 3, and step 4 is evaluate, but I'm not going to write that. Step 3. Okay. So I've shown you all parametrization before, and the parametrization is x, y, z is not r. It's v cosine u, v sine of u, v squared, where u is my angular coordinate, so it's doing 0 to 2 pi, and well, we want z to be less than 1, so z is v squared, so that's v squared less than 1, take a square root, same thing. So v is less than or equal to 1, greater than or equal to 0. That was our step 1. That's the parametrization. You can't really get started on any of these until you get your hands on a parametrization. That's where some of the money is. The second place where the money is finding the derivatives. So that was step 1. Here's 2. Got to do a partial u and a partial v. I'm going to run through these pretty quickly. So a u derivative is negative v sine u, v cosine of u, 0. And here I've got cosine of u, sine u, 2v. And now I've got to do a partial u cross partial v. All right, so, and you know, a lot of times when your parametrization has the sine and the cosine to mimic rotational symmetry, you get lots of crisscross cancellation often, and you get lots of sine squared plus cosine squared equals 1. So lots of times these calculations turn out to be kind of nice because of sine and cosine being so friendly for you. Okay, so I'm doing this pretty quickly. I'm going to get 2v squared cosine u, 2v squared sine u, and then the last one is going to turn out to be negative v. And if you don't believe me right now, just take my word for it and check on your own later that this is what you get when you do that cross product. No, that's okay. And what I have a mistake on here, that's the cross product without the absolute value. Now I've got to take the absolute value. So now the absolute value is, I'm going to factor out a v from everything, just like I did on the previous, and then I'm looking at a square root of 4v squared cosine squared plus 4v squared sine squared plus 1. Okay. And this turns out to be v root 4v squared plus 1, because the sine and cosine being your best friends again. All right. So we almost have everything. That was step 2. Let's do step 3. Don't want to hurt my I's, J's, and K's. Okay. And then my step 3 is I'm looking at f of Okay, f of x of u v, y of u v, z of u v. Remember, this is going to be just z of u v squared, and I know z of u v is merely v squared. So I've got a v squared in a squared, which is v to the fourth. And now I have all my three steps. I've got my S, my green, and my purple. And I can set the whole thing up. And it's not going to be an integral, it's doable, so we're just going to set it up and maybe ask the computer to do it. So total mass of glass is equal to, all right, we'll do a double integral. If you really want to look, I mean, this is, our formula is up here at the top. And we have found all of those. Lily says, I don't think I understand the last step. Why is F stuff equals, okay. So maybe it's hiding in here, but I'll use my highlighter again. The highlighter, look at where I've actually described F. That's where F is coming from. But typically F is just Z squared, pretty simple, but every time I see a Z, I'm replacing it with Z of UV. This is like plugging in your parametrization for a scalar surface, for like a scalar line integral. Yeah. Okay, good. So so we're doing 0 to 2 pi. Then we're doing 0 to 1. Then I'm doing my f. So I'll just, for color purposes, that's v to the fourth. And then if I want to do this in green, this is going to be the longer thing. So times v root 4v squared plus 1 du dv. And this was my dA element. This was my f. And that is how you set up this scalar surface integral. And so there will be lots of practice of these things. And that's the last of these that we'll do for a while. So now we have about 8 minutes left, unless there are any questions. So stop me if you have any questions. So we're going to take a break from parametrizing surfaces. I wanted this to take only 2 days. It took 3 days, but that's okay. Parametrizing surfaces and scalar surface integrals, I think to rush them is to do them a disservice, because they do, as you see, they take quite a long. The cross product and the magnitude of the cross product is kind of a messy process. And then Lily says, is it better to memorize the parametrization of different surfaces after we understand where they come from? No. Memorizing is going to take up too much brain space. Just from being able, really get comfortable with parameterizing any surface of revolution. I mean, after y'all get some homework, you'll feel the pattern out for surfaces of revolution, because it really just boils down to parameterizing a single variable curve in a half plane and then plugging that into the big rotation thing. I mean, that's how both this parametrization comes, that's where this one comes from, and where the previous one came from. This one, it's all that sine cosine stuff. So yeah, I'm gonna say don't spend the time to memorize. But in the last 6 minutes, we're gonna just talk about something really nice and light. It's vector fields. And I think I have this word vector fields has come out of my mouth many times, even today, and it's probably been unfair because it's like, what the heck's a vector field? What does he mean by that? So I'm actually going to say what I mean. So this is 6.1 vector fields, and these are really kind of pretty. So it's merely a vector field is at each point x, y, maybe in the plane, or x, y, z in 3D. So a vector field is at each point a vector. So this is nice. So you're still on the last page. Okay. Sorry. What? I hate that happens. Thank you. Okay, sorry. A vector field is at each point a vector. Okay, so I'll draw, for example, a quick constant vector field. So a constant vector field might be, I'm going to write v of x, y. So it's a vector that depends on points, is 1, 1. So in the plane, it's like I've got a whole bunch of points. And at every single point, I'm going to plot this vector. It doesn't change on where I am. That's really not an exciting one by any means. But let's do one that actually is more interesting. So let's do a different vector field. So v of x, y equals, let's do x comma y. So I have a vector and the components are changing depending on where I am. So let's plot some points. If I'm at the point 1, 0, 1. So my v of 0, 1 is 0, 1, just because that's kind of how I set it up. The x component, the x coordinate is the x component, and the y coordinate is the y component. So that goes straight up like this. And if you plot some other points, what happens is it kind of extends radially. This is what the vectors start to do at each point if you plotted some. And this probably rings some bells because in your brain, because this is actually, you really have dealt with vector fields before. These have been gradient vector fields. You may have heard me say that. This is similar. This is in fact, this is the gradient of f, the gradient vector field of f, where f is 1/2 x squared plus y squared. I need the half so that I don't miss that 2 coming down. But it really looks like this thing that gets bigger away from the center and it points out radially. It's like a firework. So that's a vector field because at each point, I have a vector coming out of that spot, and that vector changes depending on where I am. That is a vector field. And gradient vector fields are good examples. They're good ways to construct them. So let's do just one more and then we'll be done for the day. I'll just draw one quick little one. So let's do v of xy equals y comma x. So you got to be kind of careful. Like you can start getting mixed up pretty easily, but how to plot this. All right, well, I'm going to draw some points. And I'm going to be really careful. I'm going to make a table. So that top point is the point x, y, and I'm going to write the corresponding y, x. So if I'm at the point 0, 1, the vector should be 1, 0, and this looks like something that opens to the right. So up here, I'm opening to the right. If I'm at 0, -1, well, I got to flip them, and I've got -1, 0, and this looks like this vector. So down here, I'm pointing this way, and let's see, this is 1, 0, and this becomes 0, 1, and that looks like something that opens up vertically, something like this. And at -1, 0, flip them, and this opens down. So this goes down. And let's do a couple more. I have like 6 seconds. Okay, so at the point 1, 1, that's 1, 1, and that's out here, and that's just code that goes straight like this. In fact, you can start filling in the dots, and this is what happens. And once you have enough of them, you can sort of start figuring out how everything's going to start looking. So I'm kind of seeing curves that come down like this. They kind of go like this. Once you have like the skeleton, you really can let your intuition do the rest of it for you. And this is how you would plot this vector field. And we'll talk much more about vector fields, conservative vector fields, and scalar. So we'll do a lot of stuff in the next week about this. So I'm going to turn off my camera. Pause recording.